This is the second part in my video series opening the bonnet on the ZX Spectrum game Automania and looking at how it works down at the level of the machine code. If you've not yet seen part 1, I'd recommend starting there. In this part and the next, I'm going to take a look at what happens just before the main game loop starts. In this part, I'll be specifically looking at how the game sets up the status bar at the top here. I'll be getting right into Z80 assembly language, and although I'll try and explain some of the concepts as I go through, I'll put a link in the description to some other YouTube tutorials that I recommend to learn more about Z80 assembler. We'll look at the start game routine. This starts as soon as we hit enter on the main menu, so I'll breakpoint at the top and press enter on the menu screen. The very first line is XOR A. The Z80 processor has a number of 8-bit registers, each of which can hold a single byte and so can represent a number between 0 and 255. The most commonly used register is A, also known as the accumulator. The processor can combine bytes in different ways to make new numbers. XOR or exclusive OR is one of these ways. XOR is like asking a question for each bit. Are these two bits different? If the two bits are the same, the answer when you combine them is 0. If they're different, the answer is 1. When we combine two bytes, we're XORing each bit of the number and put them together as a byte. If we were to XOR the binary for numbers 46 and 155 together, for example, we get the binary for number 181. You may ask what happens if we XOR a number with itself. As you may have guessed, as none of the bits are different, the answer you get is 0, and will always be 0 no matter what number you start with. XOR A causes the value in A to be XORed with itself, so if we step over we see that the result is that A is 0. You may ask why the code doesn't just set A to 0. The reason for this is that the XOR A instruction uses less memory, it only takes 1 byte, whereas a typical load A with 0 instruction would take 2 bytes. The next line uses the value that's an A. When you see brackets in Z80 assembler, that generally means the contents of a memory location. So this next command sets the memory location representing the current level to the value in A, which is 0. If we hover over current level in the tool, we can see that this is stored in memory location 48367. Next, we have 3 lines that, as you can probably tell, set the score back to 0. It's the start of the game, so that makes sense. Rather than using a byte for each digit, this code makes more efficient use of memory by storing 2 digits in each byte. I'll explain how in a different video. The next line is a call. This lets the processor go to another part of the code and as a function, do something, and when it's finished come back to the line after this one. As I showed you in part 1, when we press the step over button, the processor executes all of the code in the function and stops at the next line. This time we'll press the step into button, which will let us follow what's going on inside. Let's talk a bit more about registers. I mentioned A earlier, but the processor has several others, including some named after letters. These are B, C, D, E, H and L. Each of these can hold a byte, just like A can. As I mentioned, a byte lets us represent any number from 0 to 255. So what do we do if we want to deal with numbers bigger than 255? Well, these registers can work together in pairs, B with C, D with E and H with L. Rather than treating each pair as two 8-bit numbers, we can put them together and get a 16-bit number. This lets us represent numbers from 0 all the way up to 65,535. This is handy when we want to refer to locations in the Spectrum's memory. Although the Spectrum is commonly known as a 48K machine, it has 16K of ROM that can't be changed, and 48K of RAM that can. In total, if you add ROM and RAM together, that's 64K, so actually the Spectrum always really had 64K of memory. Each memory location or address is numbered starting at 0 and ending, coincidentally, at 65,535. So what we can do is put a 16-bit number into a pair of registers, such as HL, and use this to refer to a location in the Spectrum's memory. Going back to Automania, this is what the first line does. It puts the number 49173 into the DE register pair. As we'll see in a minute, this represents a location in the Spectrum's memory, containing some data that defines how to draw the line of girders separating the status bar from the rest of the game. The next line may look like it's putting the number 512 into HL, which it is, but another way of looking at that is it's putting the number 0 into L and 2 into H. This is setting up the row and column that we want to draw at, H being row 2 and L being column 0. The game is setting those registers up, ready for the next function, which I've named Draw Scenery. This function starts drawing at the position given in H and L, and uses data starting at memory location 49173 to know what to draw. Before we step into the function and watch it line by line, I'll first look at the data it will be using. This data is structured in a specific way that will be understood by the function. The first byte at this location is 254. This tells the function that the byte after is a colour. Here it's 5, which in the Spectrum colour model represents cyan on a black background. I may do a video at some point explaining how the Spectrum represents colours, although if you remember the ZX Spectrum keyboard, 5 was the colour key for cyan. Then we have 253. This tells the function to interpret the next byte as a count of the number of times to draw the item. The next byte is 32, so the graphic we want to draw will be drawn 32 times. Then we have 6. This is an index into a table of graphics data. This one represents the girder graphic. Finally, we have 255. This tells the function that we've reached the end of this data structure. Taking this as a whole, we'd expect the routine to draw graphic item 6 32 times in cyan on a black background. Before we jump into the code, I'll clear the screen to make it easier to see what's going on. Let's watch this go through. The load A, DE instruction says read the memory location pointed out by DE and put the value into register A. As you may recall, this is 254. This next instruction compares this with 255, checking to see if it's reached the end of the data structure. Here I'll take a short digression to explain how comparisons work in Z80. Essentially it's asking the question, what would I get if I subtract this number from what's in A? It doesn't actually do this, but notes one of two things. Is the answer 0 or is the answer negative? It puts these into flags so we can make decisions based on the result. If the answer is 0, in other words the numbers are the same, it sets the 0 or Z flag. The next instruction says return if the Z flag is set, the result being that the function would finish executing here if A contained 255. It's not 255, so we keep going. However, it is 254, so on this comparison with 254, the 0 flag is set. The next instruction says that jump ahead if the 0 flag is not set, but as it is, we can ignore this jump. We read the next byte into A. As you may recall, this is the colour. We move our pointer in DE to the next memory location, and then we store the colour in the register C. Then we jump back to the top of this function again. If you're used to high-level languages, you may view this as a bit like a while loop, with the check at the top being while A is not 255. This time A is set to 253. This isn't 255 or 254, so we then jump down to the code down here. The comparison this time is with 253, so the 0 flag is set, and we carry on down. Here we read the number of repeats of the item, 32, and put this into B. We then read the index of the item to draw into A. This is 6. At this point I'm going to show you another feature of the Spectrum Analyser tool. This is the graphics view. This renders an area of memory as a graphic, so it can be used to confirm where the graphics data is in the code. If I switch the graphics view, it looks a bit like a QR code or maybe white noise. This is because the view defaults to look at memory location 0, which as I mentioned earlier is the Spectrum ROM. This is not graphics, so not surprisingly isn't much to look at. I happen to know the scenery graphics start at address 36512. Each 8x8 graphic takes up 8 bytes, so graphic 6 is at 36560. We ask the tool to display the graphic at this memory location, and as you can see it's the girder graphic that we want. Let's recap where we are. We've got the index of the graphic in A, the colour in C, the row number in H, and the column number in L. This is all the data that the function place scenery item expects. I won't go into the detail of how this works at the moment, or the video would be even longer, but effectively it copies the 8x8 graphic indexed by A to the row and column referenced by H and L, and sets the colour to C. So as you can see, if we run this once, we get a single girder graphic. That's just one item, however, and there's plenty more to draw. We increase L to move to the next column, so that's now 1. Now I'm going to take another short digression to talk about why the code uses this next command, push. We've got the index of the graphic in A, and we'll need to use that again in a minute. But we're also about to do a comparison, and the limitation of the Z80 is that in order to compare an item with a value, the item's got to be an A. So we need somewhere temporary to put the current value of A whilst we're using it for other things. To do this we have a stack. Essentially this is an area of memory the program can use as temporary storage. Data is pushed onto the stack, and later popped off back into registers. Multiple things can be pushed on, but the rule is that they can only be popped off in reverse order, so the most recent thing on is the first thing off. So here this command pushes the value of A onto the stack. You may notice this command is push AF. Actually it not only pushes A, but pushes the flags on at the same time. Next it puts the column number into A, and compares this with 32. The spectrum has 32 columns to a line, so it's doing this to work out if it's got to the last column in the line, and needs to go on to the next line. In this case we haven't, so we can skip over this bit. The program's finished using A now, so it pops back the value that we pushed into the stack earlier. A now contains the index of the graphic again, so the program's ready to draw the next graphic. The DDNZ instruction is used to repeat things multiple times. This instruction decrements B, checks if it's reached 0, and if not, jumps back to the line that I've labelled to draw a repeated item. Currently B is 32, so there's a fair way to go yet. I'll go through this code a couple more times, and as you can see, each time through we get another graphic drawn on a line. This time through, I'll step over the DGNZ, which will keep going around until B is 0, finishing the line. The code then returns to the top of the loop, but this time the data item is 255, which means the end of the data structure. The next three lines work similarly to the three lines above. DE again points to a data structure, with H and L set to the row and column. Let's take a look at the data structure. The byte of 254 again indicates the next byte's colour. This time it's 70, representing bright yellow on black. We have 10 repeats this time, and the index of the graphic is 54. Finally, there's the usual 255 representing the end of the data structure. Graphic 54 is at address 36944, so we'll look at that in the graphics view. I won't single step through the function this time as you already know how it works, but by stepping over, you can see it's drawn the timeline as defined by the data structure. Now on to the rest of the status bar. As you can see, this doesn't use the draw scenery function, but another one that I've called draw text. This uses a slightly different data structure, so let's take a look. It starts similarly with a byte of 254, meaning that the next byte is a colour. In this case it's going to be bright magenta. But 253 doesn't mean repeats this time. Instead it means that the next two bytes set the column and row at which to start drawing. In this case, row 0 and column 0. This is followed by the text to draw. Although here it looks like the text score equals, the individual bytes are used as indexes into a character set table. S, for example, is ASCII code 83 and can be found at position 83 in the character set graphics. Our character set graphics start at 34051. Let's take a look at that in the graphics view. Each character is 8 bytes, so character 83 will start at 34715. As you can see, this is the letter S in the custom character set used in the game. After the score equals, we've got another colour change, this time to white. No change to the position, and the program will write 6 zeros, the initial score. Next we have column 16, row 0, a colour of bright cyan, and the text lives equals. Then column 0, row 1, colour of bright red, and the text time equals. After this it's column 16, row 1, colour of white, and the text car equals 0. And finally 255 indicates we've reached the end of the data structure. So let's step through the draw text routine. It's very similar to draw scenery. Key difference is after the 253 byte is read. This time round the next two bytes represent column and row, so these go into L and H respectively. By the time we get to write text char, A is 83, so the letter S is written to the screen. After writing the character, L is increased by 1 to move one column to the right, and then there's another check to see if we've reached the end of the row and need to go on to the next row. Each loop through reads a subsequent byte and displays that letter. I'll breakpoint at location 49104. Now every time I hit continue, a new character is written. After score equals is finished, the C register is set to 7, and the program carries on by writing the zeros representing the starting score. The routine follows the data structure given and draws text accordingly. When it reaches the 255 byte, the function is done. To finish the status bar, the game also needs to show the number of lives remaining. Let's step into the draw lives method. It starts by setting A to 3 and writing this value into memory at 53767, which is the location the game will use to track the number of lives remaining. Although we have 3 lives, only the 2 remaining lives after this one are drawn in the status bar. So B is set to 2, and that's the number of lives to draw. The next part of the routine is setting up the data needed for the draw sprite function. Although I've named this draw sprite, these are not hardware sprites, but I've named this to differentiate the routine from the one that draws background scenery or text. This routine draws a graphic that is 16 pixels wide by 16 pixels high. There are a number of graphics of this type, and they're all stored in memory starting at address 37952. Whereas each 8x8 graphic took up 8 bytes, a 16x16 graphic is 4 times the size, so it takes up 32 bytes. Let's take a quick look at the graphics viewer to see those. If we just point the view at this address, we can tell there's some sort of pattern to the data, but it doesn't look right. That's because we're defaulting to look at the memory as a set of 8x8 patterns, whereas these graphics are 16x16. So if we change the settings down here to 16x16, it will make a lot more sense. The graphic we'll be using in this function is index 169, so if we multiply that by 32 and add this to 37952, we get 43360. That's the memory location of the life graphic that we want. The drawSprite function doesn't force graphics to be aligned on a 32x24 grid, like the drawScenery function was, but rather allows graphics to be positioned anywhere at a 256x192 pixel resolution. Each life has to be drawn at a different X position, so most of the code here is in calculating the appropriate X position. The life being drawn at the moment is given in B. Each life is 16 pixels wide, so we start by multiplying the value in B by 16. We do that here by putting it in A, and adding A to itself 4 times. The lives will be drawn from X position 160 onwards, so the code adds 160 to this value. This X position is then put into the L register. The H register is the Y position, which is set to 0. The statement here writes the 16-bit register HL to memory location 46144. As you know, each memory location is 1 byte or 8 bits, so when the processor writes a 16-bit register to memory, what actually happens is the value of L is written to the first location, 46144, and the value of H is written to the next, 46145. Next, A is set to the index of the graphic to draw. We then step over drawSprite, which draws the first graphic. Going round again, it draws the second, and the function then returns. That's the end of drawStatusBar, so this function also returns. Finally, the code initializes the music by setting HL to 34837, which is where the music data starts in memory. This address is put into memory locations 34972 and 34973, which represents the next note to play. I'll draw stumps here, but come back again for the next part in this series, in which I'll look at some more of the pre-game setup. If you have enjoyed this, please like and subscribe to see more videos about retro games from NorLogic Retro.